Hello, hello to everyone.
Hello.
Okay, Tamara is missing today. When is missing, but we still speak English for them to watch the recording. So, what we were supposed to do, you remember, we were talking about where it is, yeah, here. We were talking about exercise 15. Yeah, made the corners of the square of a position. You remember the square of a position. Every sailor is a pirate. Some sailor is a pirate. No sailor is a pirate. Some sailor is not a pirate. This is the square of a position. And we have to match those sentences to a truth condition given below. Yeah, and so let's say S is the set of sailors and P is the set of pirates. How do we represent the idea every sailor is a pirate using the following notation? So what do you say?
VI.
VIS
A.
Okay,
A set of P.
is a set of P, but can all of the sailors be pirates? Is it possible?
This is that is stated in A, no?
Yeah. So the set of sailors equals the set of pirates, right? So it's not it's not 7. It's not 6. It's which one?
Have we ever been stated that every pirate is a sailor?
Yeah. We're
Ow.
talking about every sailor is a pirate, but so we do not have every pirate is a sailor, but every sailor is a pirate. So the set of sailors is
That,
a subset, but
okay, not proper subset, but just regular subset, VII. Okay, I agree. There's big difference.
yeah. So there is a possibility that every pirate is a sailor. So we just have to include the quality of the sets in the formula. So should be number 7. Now, some sailor is a pirate.
Number 4.
Yeah, how do we read number 4?
The intersection of sets sailors and pirates is not empty. It's not empty set.
It's not an empty set. The intersection is not an empty set. Yes. Intersection. The intersection is not an empty set. Right.
By the way, we can say our previous statement as 3, because 3 and 7 are in fact equivalent.
Why?
Because 3 says that there are no such people, that they are sailors but not pirates. So it basically says that every sailor is a pirate too.
Number 3 says what intersection of sets sailors and pirates is empty.
No, not number 9, number 3.
Number
Number
three.
three.
Number 3, we have the negation there, right? P with the macron. Okay.
Number 3 says what there is no such item what is in one time and then sailor and pirate.
I mean, this one is a set of non-pirates.
Non-pirate. I don't... Да не видно мне это. Да, понятно. Окей.
Non-pirates.
Слишком
So
мелко для меня.
the intersection. Oh, sorry. The intersection of sailors and non-pirates is empty. And I think Seva must be correct here. So no sailor is a non-pirate. So I think they're equivalent. Yeah. So yes, Seva, I think you're correct here. Oh, one moment. It should be correct to, it should be an equivalent. Yeah, S and P with macron means sailors who are not pirates. Yeah. And we've got De Morgan laws. No, De Morgan laws should not be applicable here. Right. Yeah, I think you're correct. I just need to think more, but I think you're correct. No, guys. Well, we're discussing some sailor is a pirate. There are non-pirate sailors and there are pirate sailors, right?
Right.
So the intersection between the two sets is not empty, but the intersection yeah, the intersection between sailors and non-pirates not three fits. If we talk about that, the intersection between sailors and non-pirates is not empty. Is empty. No, number 3 means the intersection of sailors and non-pirates is empty. So there are no such sailors that are non-pirates. This is an equivalent to A to 7. Every sailor is a pirate. The intersection between sailors and non-pirates is empty. So number 3 is equivalent to number 7. Siava, can you see that?
Sorry, see what?
So number 3 is an equivalent of 7,
Yes,
not 4.
yes,
Yeah. Okay, we agree there. And 3 and 7 are A. Every sailor is a pirate. Yeah?
yeah.
Yeah. And some sailor is a pirate. It's number 4. So the intersection between sailors and pirates is not empty. We do not have here, or do we, the intersection. We've got 1, right? The intersection between sailors and non-pirates is not empty. This is the equivalent of number 4. Can you see that? And this is the same as to say some sailor is a pirate. Well, actually, if we're talking about some sailor is a pirate, number 4 fits because we're talking about set of sailor and set of sailors and set of pirates. We do not talk about set of sailors and set of non-pirates, though in this case they are equivalent. Yeah, same here. Though number 3 and number 7 give us a sort of equivalent, we are talking about a set of sailor and a set of pirates, sailors and pirates. So, and number 3 is discussing a set of sailors and set of non-pirates. which gives us, which leaves us only one match in A, which is 7. Okay, are we good here? Yeah. So, Seba, do you agree?
Yes.
Yeah. Okay, we're good. Now, no sailor is a pirate.
Uh,
9.
9. The intersection between sailors and pirates is empty.
Mhm.
Yeah, 9. Some sailor is not a pirate, which means there is a
Anna.
sailor.
1.
Yeah. So we've got a set of sailors and we've got a set of non-pirates, and the intersection is not empty. Yeah, I think it's 1. I agree. Okay. So these were sailors and pirates again. And we managed. And here we're finishing with the propositional logic. We're starting predicate logic. Ooh. So again, we have 3 individuals, A, B, and C. And we can call them Alex, Blake, and Casey. Any gender. And let's suppose that if we want to talk about liking, I like you, we express it as a relation R fan. Okay, and if we're talking about siblings, we express it with the relation R sib. And there are several facts about this case. Alex is male. Now, Alex is Casey's sibling. And we remember that siblings is a reciprocal relation. So if Alex is Casey's sibling, then Casey is Alex's sibling as well. So that's why we've got this. Errors on both sides. Casey likes herself. It doesn't mean that Casey is a girl. It just using, well, themselves. Yeah, themselves. Not herself. Something like that. Right. And Alex likes someone, either Casey or Blake or both. Yeah. And we're going to express it in predicate logic. A formula is a logical equivalent of a sentence, and it is a statement that can be true or false. In propositional logic, we worked with statements like P was a statement, the cat is black, or Alex is male. That was a propositional letter. Just remind. And in predicate logic, we have arguments like Alex, or, well, we have a structure within formulas. In propositional logic, we do not see any structure inside a propositional letter. And in predicate logic, there is a structure. And if we write male as a function, and we give it an argument a, it is the same as to say a is male. Okay? And as we know that Alex is male, it would be male, which takes as its variable, which takes Alex as its variable. And this gives us male A. Now, we take the relation sibling and turn it into a formula, and we've got this function sibling. And this function takes two arguments because the sibling relation is between two people. And we've got sibling, and we write variables inside A, C. Now, we can also take as relation to like and turn it into formula likes. And again, as it demands two variables, two arguments, we have two variables. And as you see, first is who likes, and second is whom. Subject and object, right? So, and as we see here, subject and object can be the same, like same person, but we still write it twice, so that the formula would work with first C as subject and second C as the object. And if we include those quantification, right? Then, well, those corners of opposition. Then we can use, help me, what do we call it? This one and this one. One is existential, and the second one is universal, right? Help me with the terms. Okay, one is existential. Okay. 1 moment, I'll check. Not to. Wait. 1 moment. If you remember, tell me. Universal, right? I was correct. Universal. So we have an existential and universal quanta, the existential and the universal. And they are sort of operators, they're quantifiers, and they should be sort of multiplied on this formula or something like that. They should be applied to the formula. So if we were talking about existing of some person, but we do not know which one, Alex or Casey or which one, we use it in this way, that there exists existential and X. There exists some. This is how we write there exists some. Some X. Then we put this dot to apply it to the likes function. And then this likes function should be written in this way, should be given arguments. And arguments are, for example, we want to say Alex likes someone. We know Alex, we know this first argument. Yeah, we know the subject, but we do not know the object. So we call it X from here. So there exists some X that participates in the relations of Alex likes X, so that Alex is a subject, X is an object. And it's read as there exists an X such that first part Alex, formula likes, second part X. There exists an X such that R likes X. Okay. Right. So we have predicates, and this is the basic expression, predicate, which matches the idea that predicate lies in the basis of a statement, of a sentence. So that is why we more or less build the whole expression around the predicate, around its predicate. So, and if you remember the theory of syntactic roles, predicates have valences. There are predicates that have only one free place, one valency, and we call those verbs intransitive, like I sit. Yeah, I cannot say I sit whom. I cannot sit whom. This is the idea of transitivity and transitivity. So there are intransitive verbs that do not have, that cannot take object. They only have a subject, right? I'm trying here to show that behind this logic, real linguistics, like language reality, exists. So, and as we have valences with verbs, predicates in logic, in predicate logic, can be unary predicate symbols with only one argument. They can take only one argument. And binary predicate symbols, like transitive verbs, that take two arguments. And in predicate logic, we have predicates and we have names. So, and also we have variables, and most commonly they use X and Y, but it might be any other variables. I mean, you cannot take M or N. It's just tradition that for variables, X and Y are taken, same as in math. Variables is the same as Alex likes someone who do not know who. It is the whole set of people that Alex likes. So, anyone. And this is a variable. And we have quantifiers. It's kvantary in Russian. Quantifiers, existential quantifier, and universal quantifier. Existential quantifier for some, universal quantifier for all, for everyone. Universal, everything. And in predicate logic, we compose those symbols to express statements, to form statements. And same as in propositional logic, formulas can be very simple, atomic, or they can contain other formulas. So we've got formulas P A, we've got formulas P A B, and so on. And we can include logic operators here. So we can take two formulas and join them in a new formula. And we can use such things as negation in our formulas. Yeah? Siblings AB and not siblings AB. And it is funny that this thing is a logical contradiction that renders true in no model. Yeah, we discussed contradictions recently. But still, it is a well-formed formula. Yeah, so a syntactically well-formed formula in predicate logic is independent of whether it is true in any particular case or whether it could be true in any case. Which is actually well represented in Noam Chomsky's formula, green ideas are fiercely asleep, or something. Yeah, something like that. So it's still a well-formed sentence, right? Though it contradicts the reality. Right. Existential and universal quantifiers make existential or universal formulas with variables. And we form a new formula. There exists some x such that A likes X. We have three parts here in the existential formula. Quantificational formula, it's called as well. And the three parts are the existential quantifier, the variable which is bound by the existential quantifier in this formula. So it's connected to existential quantifier, and existential quantifier influences this X more or less. And the third part is the whole formula, where the variable appears. Okay. Questions here? Is everything clear? No. I hope so. So, the basic expressions of predicate logic include constants like A, Alex, and variables like X. Constants, constant things, constant expressions might be divided into two sorts. First, individual constants, which is names, Alex, Casey, Leonia, Sonia, and predicates, male, X, sibling, XY, XY, I don't know, white, X, they are predicates. And first thing, we're talking about individual constants, also known as names. Yeah, typically A and B, but it can be any other letter, of course, or any other big name. But normally, if we have a long name, Saint Smith, which is written without spaces, which is important, no spaces in a constant. Normally, people take the first symbol of this name, write it with a big letter, and this is it. I mean, it's okay if you write Alex as a name, or you write R, but normally it would be smaller R. Yeah, or you can write the whole name, including surname and family name, but you must join it with the underlining sign. Al, Eaton, something like that. That would be name. Right. Now, variables. As we've already discussed it, as we've already said, normally variables are X, Y, or Z. Well, sometimes, very frequently, semanticists use what's it in English? I forgot. This subscript like E, and this helps divide different X's from different sets. For example, X from set of sailors and X from set of pirates. And they also use prime marks or double prime, X prime, X double prime. It's just the way they write those variables. And And variables behave as very similar to individual constants. Because in fact, every individual constant, like Alex, is a part of a set of, I don't know, certain type of people. And we can always take another person from this set. He won't be Alex, but he would be the same person, the same type of person. So he would behave same as Alex. So the variables occur in the argument position of a predicate. This is the argument position of a predicate. So a variable is an argument to a predicate. Because both variables and individual constants are terms. Well, it's not quantifiers, it's individual constants. Variables can appear in one place where individual constants cannot appear, right after a universal or existential quantifier. Because when we say all of them, or when we say some of the set, we do not mean a certain person, right? We mean some. So it might be this or this or this. And so after a universal or existential quantifier, only a variable can stand. So it mostly there exists some x or all of y or some of z. This is a type of quantification operator. Right. Are we good here? Yeah.
Yes.
Now, predicates. Predicates define properties. Being female, being Swedish, being white for an animal, for example, or for example, my printer is white. It's a property of my printer. So we would say white. Something is white. Or if we're using verbs, sitting is a property, or sitting on the chair is a property. Like anything. Yeah, but also predicates stand for relation, like loving, relations meaning a relation between two people, being sibling, yeah, being between two people. These are relations. So properties or relation. So something, properties is something that defines X in some way, and relation is when X is somehow related to some other Y, Y. Yeah. And predicates is what I'm just repeating myself to make it clear. Sorry. And predicates is what stands for both, either property or relation. So, and we have valence, yeah, but same as with the verbs. Yeah, we discussed that. Valence is ability of a predicate to combine a certain number of terms, certain number of individual constants or variables. Unary predicates take only one term. Intransitive verbs do the same, right? So their balance is 1. Binary predicates have valence of 2. But a predicate can take more, and we have ternary predicate with a valence of 3. For example, there is this predicate between, and it's a ternary predicate because it defines that some x stands between y and z. So we have 3 terms, and we would write it as, it's always written in capital letters. Predicates between and then we write x that stands between y and z. And this is a ternary predicate. Yeah, so it denotes a relation that holds of 3 objects. The trend is true of concerning, well, if we are talking about those 3 objects, this relation renders true if and only if x is between y and z. Yeah, and actually there can be any value of valence. The row can be anyhow long, no upper limit. Yeah. Okay, and this is enough for us so far to talk. This is enough for us at this place to talk about predicates as unary predicates that take one term, binary predicates that take 2 terms, ternary predicates that take 3 terms, and that it can be more. The quantity of terms that a predicate takes. Right. Are we good here? So far? So far, so good? Yeah, so far, so good. Okay, I mean, normally the right predicate in as here in capital letters, but if you write them in lowercase, probably doesn't change anything. Right. Now, syntax of predication. Yeah. This is an atomic formula, basic one. It is a unary predicate that combines with a single term. Combines meaning we take this individual constant or name and we combine it with a predicate. Yeah, so, and we get this formula, which is atomic. So, right. And examples of atomic formulas are here. Male A, sibling YY, likes X, C, and sibling and likes are binary predicates. Okay. Now, if 2 terms refer to the same individual, for example, we can call Lyonya linguist, right? And linguist is not, let's say it's a name, okay? If it's a name. But they both refer to Lyonya, to this person sitting over there, looking at me through Zoom. So, 2 different terms, 2 different names can refer to one individual, the same individual. And then we have equality, and we can equal those 2 names, those 2 terms. So, Lyonya equals linguist. For example, their names. Linguist is not a predicate here. And technically, this equality symbol, which gives us identity, technically it's a binary predicate because it's something that combines 2 terms, right? But it behaves differently from all the other predicates. Syntactically, the identity symbol is used to form atomic formulas by joining 2 terms. It's inserted between the 2 terms and not in front of them as all the other predicates. So we're thinking about this equality term, equality symbol as a kind of predicate, but a very special kind of predicate. that stands between two terms, is written between two terms. But still it is an atomic formula. Right. And equality sign, equality symbol can stand only between terms. In order to combine two formulas, we use the biconditional symbol. Biconditional symbol. Right. Yeah. Now, as we've already seen in propositional logic, if phi is a formula, then negation phi is also a formula. And we have other ways to connect formulas with binary connectors. Phi and C, phi or C. If phi, then C. If phi, if and only if C. We've already worked with that. Okay. Nothing new here, right? Right. Go on. Yeah. Now, syntax of quantifier. Given any variable u, remember that it can be x, y, z, or anything. It's just u here. If phi is a formula, then we add the quantifier all u such that phi. And this is also a form. Some u such that phi. This is also a formula. Right. For example, all x, and then we need a formula here, such that x is happy. Yeah. Gives us a well-formed formula. All x such that x is happy. This is a formula. And actually this stands for all happy x's. Or all happy people would be written like that. Or if we are taking the set of sailors, all happy sailors. Right. Now, there is this rule about the dot. Basically, we write universal quantifier or existential quantifier x dot and then the formula predicate arguments of the predicate. But this dot can be omitted, dropped. We can just write all x and then the formula. This is actually X is happy if X is friend. A moment. If X is happy, then X is friendly. Yeah. So with the quantifier, all X that are friendly when they are happy. This is what this formula means. Yeah. And this part that stands before the quantifier is called the scope of the quantifier. Do you remember we discussed the scope of negation? Yeah, do you understand what I'm talking about? I mean, it's not that okay. I like apples. I let me see. I don't like apples. I like not apples, or I don't like apples. Different scopes. I don't like apples. The scope is over the whole sentence. Yeah. And I like not apples. The scope is over the apple only. Yeah. Do you remember that, or should I draw the concept of scope? No. Sonia, Seva. Are we good with the concept of scope?
Yes.
Yeah. Okay. So, what stands in those brackets after the quantifier is the scope of this quantifier. And when we write those brackets, we do not need the dot. But if we drop the brackets, then we need this dot. Yeah, you see? Dot works as brackets. Yeah, indicates that the scope of its quantifier extends as far to the right as possible. If we write the dot. Okay. When we do not have a quantifier here, X is not bound by the quantifier. So X is free. X is not bound. Yeah, if we have this quantifier here, X is bound by the universal quantifier here. So we have open and closed formulas. Open formula contains at least one free variable, not bound by a quantifier. And a closed formula contains no free variables. All of the variables are bound by quantifiers. And this closed formula is also called a sentence. Yeah. So In an atomic formula, any variable is free, no bounding by quantifiers. And free variables in a formula are also free in the negated formula. And when other operators are applied. Yeah. And a quantifier bounds a variable only if, or only that variable that stands in the formula. So in the expression universal quantifier x, happy x, friendly x, x is the bound variable. If we would have y over here, well, it's so I'm not sure if it's possible. If we've got y in the formula, y would be free variable, right? You see, because bound variable is x here. Are we good?
Mm-hmm.
Yeah. Right. Now, exercise. Which of those are well-formed formulas? Okay, you're thinking, right? I hope you're thinking.
Sorry, could you scroll up to the definition, please?
To which definitions?
Of L.
L-pred is predicate logic. So which of these are just well-formed formulas in predicate logic?
Okay.
We need to find the definition of well-formed formulas, I guess. Did we have it? I'm not sure there was a definition of well-formed formula. It was just discussed. Yeah. So what do you think? B is well-formed, right? Everything's good here. Happy, someone is happy. Happy is a unitary predicate. it should take one argument. Happy B is a well-formed formula.
And C, I suppose no, because happy is unary predicate, it is not binary.
Hmm.
Mm-hmm. Yeah, I agree. C is happy is unary, so and look, loves is normally binary. It's a binary predicate, right? But we are not. Well, syntactically, we are fine if it's XX, right? Because X can love himself, right?
Yes.
Yeah. So G looks like a well-formed formula to me. And F, I, and J have free variables, right? Unused variables, not bound by quantifiers. But it's okay. It doesn't contradict the structure of a well-formed formula. It gives us open formulas, but still the formula is good, right? Double negation is allowed as well. And as negation of a formula is a formula, then double negation is a formula as well. Yeah. Are there any other not well-formed formulas but C? I think all the others are good. What do you say? What do you say? What do you think? Happy A and happy A gives us true, like always, right? But it's still a well-formed formula syntactical. I mean, it gives us true in all cases when A is happy. Okay, guys, do you agree that all the others look good? I would say so. Yeah, and we've already discussed the formulas that have free variables, right? We've got f with a free variable y. We have I with a free variable z, and we have j with the free variable m. In H, both x and z are bounded by quantifiers. Yeah, and in this case, if we have two or more variables bound, each of them is bounded by quantifier, then we write it with dots. There is such an x and there is such a z, such that x loves that. Yeah, something like that. Right. Okay, exercise 2. Which of the following symbols are terms? This is easy. Yeah, terms are things that can serve as the argument to a predicate. X is a term or not? Can X be a predicate's argument? Guys, are we good? Right. Imagine a predicate. Let's say predicate love. Yeah, loves. It's a binary predicate. So it takes some person who is the subject of this love, and it takes some object that is the object of this love. And we read it as X loves Y. Okay, are we good? Now, in this predicate, what are arguments of the predicate? What do we call argument? Sonia, Seva, guys, hello. Are you really indeed good with all those terms that we discussed above? Look at the text. That's easy. Guys, do you really need me to repeat? Sonia, Seva. Okay. I feel like I'm ghosted a bit. But okay, Lenya, do you understand that this is a predicate?
Yes, indeed.
Good. Do you understand that it's read like X loves Y? Okay.
Yeah.
We have the predicate here, right? Now, this predicate takes arguments. And these are arguments. arguments is what we apply to this predicate to get the sentence. Yeah, like a verb, transitive verb has valences and it takes subject and object, X and Y. Peter loves mushroom. Okay? Right. So this is a predicate and these are arguments of this predicate. So can X be serve as the argument to predicate?
Yeah.
Yeah,
Okay.
can
Yeah. Yeah.
easily. That can
Yeah.
be an argument. Now, can a name like Alex serve as the argument to a predicate?
Yeah.
Yeah, we can put it over here and then it would be Alex loves someone, right? Well, not someone, but why? Okay, can sibling X serve as the argument to a predicate? This one should be tricky.
Mm. I don't think so.
Sonia, what do you think?
Sibling is a predicate. So,
It's a formula. Predicate is sibling. Sibling X is a formula that combines predicate and its argument, right? Can we use formula as an argument to a predicate? This is a not well formed thing. Can you see that? Sibling demands two arguments. So, yeah. But if we take this one, which is well formed, this is a formula. Yeah, we can use phi for this formula. And a formula, as far as I understand, check me, can serve as an argument to a predicate. Okay? Same as we can add, we can use operators like and or and if and only if with formulas. Yeah, you remember that. So I understand that the formula can serve as the argument to a predicate. So it's a term. But can predicate serve as the argument to a predicate? No. No, predicate cannot be a term. No. What about a negation, an operator? Can it be a term? No, it's not a term. What about this operator? Quantifier. Can universal quantifier be a term? No. Yeah, C and Z same as A and X, right? And X and Y is a formula. So same as sibling, right? So we have X, A, C, Z, sibling XA, X and Y as possible arguments to predicate. Ooh, exercise 3 is for home. Was it difficult? Not really. And this is the way how we can write down the structure of a sentence. So thank you for coming and listening to me. Any comments? You're unusually silent today, guys.
Thank you.
Thank you.
Very much.
See you in a week, and exercise 3 for the homework. Have a good day. Shavua tov. נראה בשבוע.